All right, people, like you heard, today we're going to be talking mostly about advanced manufacturing. Now, before we get started with today's episode, let's talk about today's sponsor, and that would be Mouser Electronics. Over here at the Next Byte Podcast, we love Mouser.
We love Mouser.
Why do we love Mouser, Daniel?
They are not only at the nexus of understanding where interesting technology, where the tires meet the tracks, so to speak, because they're one of the world's largest and most reliable electronics distributors. They're also really well connected to the folks developing the technology.
Absolutely.
The folks in academics, the folks at these cutting edge companies, startups, et cetera, that are developing technology and putting it out into the real world. Mouser's kind of at this awesome intersection of the two places where they can sit there and go, we understand what technology you need to build with, and we can also understand what technology is coming down the pipeline. And they write awesome articles to help teach us about, all the interesting tech that's flowing through that pipeline.
Exactly. And one of the favorite groupings of content that they come up with, for me at least, is these, let's call them primers. All these wonderful technologies are developing right before our eyes, and there's just almost too much to learn about in a short amount of time. Well, Mouser's team really comes up with these wonderful, like TLDR, easy to digest, relatable content about, the breakthroughs. And today, the one that we're going to be linking in the show notes is talking about PCB production. So, if you're developing an electronic device or you're trying to do a mechatronic project, you are going to have electronics on board. And if you want to do it custom, you're going to have a PCB. That's the board that houses all those little components on there.
A printed circuit board.
And the common method of creating these PCBs is you make a design, it goes to some board house that has, these massive sheets, they cut out what you want, they build it exactly to your specs, and that's wonderful, but obviously it has a lot of lead times, it can be costly, depending on how much, the scale that you're producing at. And it's kind of weird to still have that be the norm, given that if you look at its mechanical counterpart, shout out to the mechanical engineers listening. Daniel and I are mechanical engineers.
We
have
feel
love. Yeah, we feel you guys. Additive manufacturing has become the norm for these like rapid prototyping or just project building, where you have a unit that can just reside on a desk, creating the part that you want. Well, the same thing can now be done for PCBs. You have these desktop PCB production units, and there's so much that you can do. You can rapidly prototype. They're convenient. Obviously, they have some drawbacks. You can't scale them like you would for a production part, but you get a lot of the benefits that you got out of the early versions of these 3D printers that companies were leveraging before it reached the average consumer.
And a little bit of a spoiler alert, right? We're talking about a team from MIT today that's using precision 3D printing. And by 3D printing, we're also talking about printing electronics, circuit board printing. It's very similar to this topic here, where they've been able to overcome some of these cons associated with desktop PCB manufacturing, and they're able to do some pretty interesting stuff with it. But that's why we thought these two topics tied together so well.
Absolutely. And now that's actually a pretty good segue. Let's get into today's article. Like you mentioned, we're going to be talking about researchers associated with MIT, but they're actually a startup as well called Volterra. And what their focus is on is creating field electron emitters. Now, what is a field electron emitter?
It took a lot of research for us to be able to wrap our heads around this.
We even had to think on it. We're just like, hey, my understanding is this. Is your understanding this?
I'll be honest, guys. Usually we just go at this raw. We jump in organically. We're like, yeah, we both understand this. We're going to talk about it. This time we had to pre-marinate a little bit, make sure that we were on the same page. But my understanding, and I think for Bode's understanding as well, is that field electron emitters are these cool little devices that basically are designed to shoot out a very direct, small stream of electrons when an electric field is applied to it. And basically it works through a process called field electron emission, where electrons are able to jump out from a solid surface into a vacuum. And the way that they achieve that is by having a very, very specific geometry to this flat surface that gets charged with an electric field. And then also it converges to a really, really small tip. And on that small tip is where the electrons are shot out from it. The way that I saw an awesome analogy on the internet. It says like the most understandable metaphor for this is like, imagine if you have a giant balloon filled with air and then you poke a tiny little hole in it and then you squeeze the balloon to force air out of the tiny hole in the balloon. This is very similar. You've got an electric field forcing pressure, creating pressure,
the squeeze
for these electrons, and the electrons are the gas, and it's like you squeezing on this balloon to shoot air out of it. Very similarly, applying an electric field to the solid surface that's got a little tiny tip at the end where the electrons are allowed to shoot out of. It's very similar to the tiny hole in the balloon.
Mm-hmm.
When the electric field is applied, it shoots a small stream of electrons out from the surface into a vacuum. Sounds interesting enough, I guess.
But why is it important?
Without context, right? It's challenging to understand what exactly this is used for.
Yeah.
It's already being used in mass spectrometry, so it helps measure gases really well. It also is being used in certain types of scanning electrode X-ray machines. They use these tiny streams of electrodes to etch tiny patterns on materials, etc. But I think one of the most interesting applications, at least that we could both put our heads together, and this team from MIT as well, is that it can be used along with a stream of positively charged ions to create really, really small, miniaturized propulsion jets for satellites in space. So think about a tiny CubeSat, something that could, fit on your desk as opposed to something that's the size of a shed. And you could build this and tinker with this on your own. If you have the ability to create a field electron emitter, you also have the ability to add a thruster onto this small, tiny cube satellite and allow electricity as a method of being able to force this thing through space as opposed to combusting a gas.
Yeah. Yeah. I mean, you hit the nail on the head. But what kind of struck me is, well, this sounds so promising as a piece of tech. Why isn't it like very commonly used? And it really just comes down to the fact that these are quite difficult to manufacture. Typically, you require like some pretty advanced clean rooms where you do semiconductor manufacturing. In the US, I think we have 1 or 2 level 1 clean rooms that are like super, super clean rooms. And getting one set up costs like in the hundreds of millions, if not billions of dollars. So that's already a blocker. And the production techniques used to create these field electron emitters, I'm just going to use them, call them FEE moving forward. These FEEs, they're slow and they take a lot of time. So that adds to the cost. That usually the manufacturing has been the bottleneck. Well, within the world of people that care about FEEs, there's been this thought of, well, additive manufacturing has advanced quite a bit. Could we leverage that to kind of reduce the manufacturing burdens a little bit? And this process of direct ink writing, which is kind of like layering ink until you get the geometry you want. It's kind of like FDM, fused deposition molding, but for ink instead. It's been used to come up with an FEE that could compete with the ones that you get out of a clean room. But unfortunately, they just can't. They're not as high enough performance. They suffer from low, what was that? Current density.
Yeah.
Low current density. And at the end of the day, the applications where you are using these FEEs, they are less cost sensitive as they are performance sensitive. So they're willing to have the lead times and the high cost as long as they get the performance they want. So that's kind of the state that we have generally been in for some time. Where this team steps in is by going, okay, we don't want to just give up on this additive manufacturing approach. What are the issues there and how do we solve them?
Yeah, and you mentioned a little bit earlier, but they use this awesome special 3D printer that specializes in doing desktop PCB manufacturing called the Volterra Nova. And this is kind of their main tool that they're using to attack this. I want to do a quick plug for this. The Volterra Nova is actually a startup founded by 4 college students from Waterloo 9 years ago, and they created it as their senior design project. And they turned this into this awesome startup that's now got viability out in the world. And you've got state-of-the-art researchers at MIT using this to help manufacture something that hopefully has an impact in space propulsion in the future. So all this to say, we've got a very strong passion for Bode and I because we met doing student research and doing student projects while we were in college together. But just another testament, folks, your senior design capstone project may be worth something. It may be worth lots of some things if you end up creating a solution, a 3D printer that can create PCBs on the desktop and do it in a reliable manner.
That's a great point, yeah.
Sorry to divert us from the main conversation there, but appreciate that this came from a student design project.
Me too.
As a bunch of students from Waterloo. We know, Waterloo's a bunch of smarties up there and our upstairs neighbors in Canada, but
The Canadian MIT.
yeah.
And it's...
Or MIT's the American Waterloo.
Oh, that's a good point. What I was going to say is, we're big advocates of helping students do, more advanced research. Don't just like artificially limit them. So it's great to see, like, we have evidence now to kind of bolden that claim a little bit. But I guess moving into the 3D printer discussions with Volterra, like you said, they have this platform that seems to be capable of a lot of these high performance additive manufacturing requirements. And this team at MIT was like, okay, from what we can tell, the carbon nanotubes are like the active agent that could help with that current density of the FEEs. And if we could just increase its content, we could increase the peak current emissions or emission currents. And they were like, well, when we're making the ink that's actually going to go into the printer, while we're mixing these carbon nanotubes, which is the active ingredient, with the other materials like water as the coolant, if we can use sonication, which is a fancy term for just using sound waves to mix stuff, they can prevent the solvents from evaporating too quickly.
I like that, sonication.
Sonication?
Yeah. We're sonicating people's ears right now.
That's true. But I got to be honest with you, where my brain went the first time I read this was Sonic, like the fast food joint that you can just...
I thought you were going to say Sonic, like
the hedgehog?
Yeah, the hedgehog.
No. I'm unfortunately too in love with the average American burger to care about video games
with the subpar American burger.
I mean, it hits.
It does.
Yeah. And the slushies, don't get me started. But anyways, yeah, they were like, hey, we could use sonication, make sure that the solvents aren't evaporating as quickly. And then towards the end of the process, filtering out the non-dispersed carbon nanotubes and then adding the clumps.
Yeah.
Yes. And then they were adding the ethyl something.
Ethyl cellulose.
I didn't want to say it. Yeah, you got it. That is the other active agent that's within this ink. So that sonication was like their bread and butter, their secret sauce that was keeping this ink as healthy as possible before they started the manufacturing process, right? And then, drum roll please, they started printing.
Yeah.
But they were like, I wonder how much we can really push this printer to its limits, because there is a limit of how much of these carbon nanotubes you can have in your ink before you start clogging the nozzle. So they're like, let's just test different like weight percentages for both the carbon nanotubes and the ethyl cellulose and see what is the best we can do without, killing this printer. And that's exactly what they did.
Well, and I think it's important to mention here, like, I appreciate the problem-solving approach here, saying, what are the constraints with the current 3D printed solution? Why doesn't it work? Well, there's not enough carbon nanotubes in the ink. So they understand what some of the challenges were with developing a carbon nanotube ink with high loading percentage. And when we say high, I'm guessing it's probably in like the 3 to 5% range, because they ended up landing on 4%.
4, yeah.
But 4% by weight, adding enough carbon nanotubes to this liquid ink was clogging the nozzles. So they found a way of improving the way that it's mixed using sonication, and also added ethyl cellulose, which helps make it more stable, and then pushed this state-of-the-art printer to its limits and just said, if we know carbon nanotubes can help with the performance, let's go to the actual physical limit of our manufacturing technology. Let's do the best we can to improve based off the previous constraints, previous understandings. And I appreciate that they went all the way back to scratch and like started from the ground up. We're going to develop our own material to do this. And it's something that I saw also when I worked at Tesla, is it felt like when we ran into like a hard wall about like what was possible, the common tendency there was to be like, okay, well, if our equipment can't do it and the current technology can't do it, we must invent a new material to solve the problem properly. And I appreciate that they did a really similar thing here at MIT, which is like they challenged the fundamentals of the problem using first principles thinking. And in this case, they invented a new ink that when they put it through this printer, they landed on about 4% weight percentage. They ended up printing something, again, a little bit of a spoiler alert, but they ended up printing something that performs way better than the previously 3D printed counterparts. And actually, in some ways, performs better than the current state of the art that's made in a clean room. And it costs less, and it takes a lot less time to manufacture. What was the cycle time on this?
30 seconds.
Yeah, 30 seconds to print it using this desktop 3D printer. And again, all that's unlocked by just like going back to the basics, trying to break the rules. And in this case, they broke the rules by inventing a new material to start this process with.
Yeah, and the benefit of using this Volterra platform, the Nova platform, is you get a lot of options with the substrates to use. You get a lot of options with the inks to use, and it's fairly portable, especially when you compare it to a clean room. So more people can access this manufacturing methodology and tinker with it, and essentially create new FEEs whenever, like, on demand.
Yeah, and so what here to compare this to other 3D printed state-of-the-art field emission devices, they were able to achieve 35% lower startup voltage, which means it requires less power overall to get the field emitter going. And successfully emitting electrons. And then it also was able to achieve 65% larger current density, which means that they're able to get more electrons shooting out. So essentially, right, outperforming any of these state-of-the-art or the 3D printed solutions prior to their invention of this new ink and using it with the Volterra Nova. Again, just kind of to zoom out and the so what here, they've outperformed other printed emitters. They've outperformed in some ways current state-of-the-art. The Nova printer allows them to do printing on a board that they've designed for other purposes with other geometries, and you can do the printing as one of the last steps. It only takes 30 seconds. And again, we said this has an impact in space propulsion, has an impact in all sorts of like high-tech instruments like mass spectrometry, scanning electron microscopes, X-ray machines, etc. And it all starts with them trying to challenge the fundamental assumptions here. Is like, why is this so hard to make? Why is it so expensive? Why does it cost so much? Why does it take so long? Why can't we just do this with a desktop 3D printer? So they went and did it. And
they did it better.
Yeah.
Which is incredible. So, like, I guess to just kind of sum up this episode, field electron emitters, you probably don't know what they are. You probably don't care. At a very basic, simple level, you apply an electric field to these devices and they output electrons into a vacuum. They're used in these, high performance instruments like mass spectrometers that tell you what percentage of every element there is in whatever you're looking at. They can be used for X-rays, and I guess more ambitiously, they can be used for space travel. But these things are actually kind of expensive. You got to have these incredible clean rooms to create them. It takes a lot of time to manufacture them. And a lot of people have been wondering if we could just start using additive manufacturing. And they've taken stabs at it. But unfortunately, the parts they come up with are just not as high performance enough. Well, in comes these incredible team of researchers at MIT working with this Volterra startup that has a ink-based 3D printer. And they start experimenting with the actual ink composition because they realize that's where the bottleneck is. They formulate a new ink. They print it with different weight percentages, the concentration of the active ingredients in there. And they actually end up making something that's better than the expensive stuff coming out of a clean room within 30 seconds. Like, it takes 30 seconds to print these things.
Literally 30 seconds.
And that's why they've changed the name of the game when it comes to FEEs.
I love it.
Yeah.
So before we wrap up here, two things. I want to say a quick domo arigato to our friends in Japan.
Are we getting sushi this weekend?
Thanks to our friends for listening. Top 200 podcast in Japan.
Incredible.
I appreciate that. And yeah, I guess we've been selective about which countries we actually go try on their food, but you can absolutely get me to eat some sushi to celebrate trending in Japan. I appreciate that.
I've only begun my sushi eating adventures this year, actually, so it's perfect timing.
Yeah, and maybe eventually we'll be traveling to Japan to
wonderful
mainly try the food, but also talk about interesting and impactful technology.
Of course.
The other thing I want to mention is we've recently launched a newsletter. We've worked really hard to get good at communicating technology to you in the audio format. And one of the things we're working on now is trying to deliver the same value, if not more, in a written format. So we would appreciate, folks, if you go check out the link in our show notes, or you can go type it into your search bar if you want right now, read.thenextbyte.com. Take a couple seconds to sign up. We hope you trust us with your email. We're doing our best, like I said, to deliver a lot of value, communicating interesting technology to you in a way that's easy to understand. And one of the best ways, if you already like the podcast, to achieve that is also by signing up for our newsletter.
Amazing. Folks, thank you so much for listening. As always, we'll catch you in the next one.
Peace.